All right. So next, since we have dealt with assembly, we also can't leave event handling alone. So there are actually two instructions that will be useful for the next lab, actually. And these instructions are used for synchronization. One of them is called wait for event. And all it does is it puts the ARM processor into a low power mode, and it just waits around until either a send event, which is the next instruction that I have down here, either the send event occurs or a physical IRQ, FIQ, or an asynchronous abort occurs. So if either of these events occur, then it wakes up. It keeps sleeping. So. And this is used primarily to synchronize different pieces of code and across multiple cores, even so. And it's used for spin locks. Next, we'll talk about some exclusive instructions. So the two exclusive instructions are called load LDR-EX, which is load exclusive, and STR-EX, which is store exclusive. Prior to ARM v6, mostly there were only two atomic instructions available. So if you remember exchange from x86, there used to be something called swap and swap byte, which was SWPB. But now it's been deprecated in the sense that it's still available, but it's not used as much as load exclusive, store exclusive. The reason is because the swap was implemented as a read-locked write, which means it doesn't allow you to read the value until it's finished writing to it. So the idea was if you swap something, only after the swap occurred could you actually access the values, right? The problem was between the read lock and the write, you weren't able to do any operations in your assembly code. So if you wanted to implement something like a semaphore or something like that, you weren't able to do that. So so that's why they came up with these load exclusive, store exclusive, and I'll go into how they work a bit. So the BDH here is just for byte, double word, or half word. And that actually allows you to do 64 bits, I guess, 2 words at a time. And let's go to the next one. So there's no access to memory allowed between the load exclusive, store exclusive instructions, but you can actually write code in between them to do other things, as we'll see in Lab 5. So after starting a load exclusive, if you want to abort the exclusive operation for any reason, you can use the clear exclusive, CLR-EX operation. And you can also use the data memory barrier, which is one of the earlier instructions we had looked at. And this was for, this actually, what it does is it only allows access to registers on that one processor. So the memory barrier is only applicable to the processor that it's running on. And so other processors could technically, I guess, continue accessing their registers, or they could access this core's registers. And this is actually used mostly on the one core of that one processor. So the data memory barrier, as I mentioned earlier, again, it ensures the correct order of operations or memory accesses, and it only after it's finished you can turn off the data memory barrier using the send event, actually. So we'll see that in the atomic lab. So you guys go into your emulator. Let's see if I can share it. If you go into projects and then atomic, so here you'll see two files, atomic.c and then mutex.s. So the goal of this lab is to implement the mutex using the load exclusive, store exclusive instructions, and the atomic.c actually just has libpthread code, so it essentially creates two threads that are actually the same function called do something. So if you look at atomic.c, it's using the pthread library that you see included up top here. So, and all it's doing is it's creating in the main function, creates two threads that call the same method. But it also calls two methods, which is up here. So there's lock mutex and then unlock mutex. So this is to sort of ensure, this is sort of like a semaphore, I guess, if you will. So where only one thread can get into this section of code, execute it, and then return. So this is the method do something. And here are the two threads that are started. So all you'll need to do is actually modify the mutex locking and unlocking mechanism here. So you have to use load exclusive, store exclusive instructions in between this and here. So I've actually included the solution. But and this is actually an example that ARM provides. So, and this is not the best way of implementing a mutex. Just putting that up. But it is a way. So here's sort of the pseudocode for how you go about locking the mutex using load exclusive and store exclusive. And mutex unlock is actually the easiest. Actually, if you'll see in your assembly mutex code, there's actually a variable for unlock value. So, it's called equals unlocked. So you can use that. So once you've written the code, you can actually type make and run the executable. Test it out. So as compared to my notes, I believe the architecture reference manual is given, and that's probably going to be more helpful for looking at how these instructions work. Yeah, just another quick announcement. If you guys want to save all your work at the end of the class, I would recommend that you use the SSH folder that we set up inside the VM. So if you go to like places, ARM, and all you have to do actually is copy the root, then projects. So this has all your labs, except for the interrupts lab. And for the interrupts lab, actually, if you go to your home folder on the VM, there's a projects directory, and then copy, I believe you'll need interrupts. and just grab the code. And what I can do is I can post this VM on temp space, and then you can actually copy those folders back into the VM, so it'll keep your work, essentially. And if you still haven't figured it out by now, the solutions are in the .solutions directory, the projects folder, on the VM. So there are actually two things I'd like to highlight. So in the manual, if you actually look at exclusive access, you'll see that the store exclusive instruction actually returns a value into the destination register. If the store exclusive is successful, it actually puts a value of 0. And if it's not successful, its value is 1. And so essentially what they've done is they've taken the swap instruction, which takes the read lock write, and kind of separated it into this load exclusive, which is sort of the read lock piece, and then the store exclusive, which is also sort of a write lock. And so if you actually go to the page 688, the store exclusive instruction takes the actual memory location you want to write to in a register, and what value you want to write, and then finally, if the store is actually successful, it writes the 0 or 1 into this destination register. So that's sort of the usage for store exclusive. Load exclusive only takes 2 registers, which is the base address of the memory location you want to write to, and the actual value that you or the register that you want to load into. So that's why if you actually take this. So sort of the pseudocode, and this is sort of based on what Arn came up with. So if you have a better solution, please do let me know. So essentially the mutex lock function. So a mutex tries to allow access in a safe manner to a critical section of code, right, that's shared between 2 processes. So that's what a mutex does. And if you look at the code under atomic.c, so here. So if you look in atomic.c, you'll notice that there's an argument being passed to lock mutex, and it's called mutex locks, and it's defined as an unsigned integer up here, and it's initially set to the value unlocked, which is defined to be 0, and locked, which is defined to be 1. So this is just for convention, but those values could be anything. So the idea is that do something is a critical section of code, and you want to order the processes that get access to this function, essentially. And once that process is done, it unlocks the mutex and allows the other one to enter, essentially. In order to do this, I actually slightly modified the solution, but it still works. So the idea is your pseudocode is to loop and try to get an exclusive read lock on the argument that's passed into mutex lock. So if you're able to read it, then you know that you can write to it. That's why you end up first loading the locked value here, You can choose to do it this way, or you can actually choose to use constants there instead of using equals locked and equals unlocked. You can just use constants in its place. I just thought this would be more descriptive. So this equals locked is actually a memory location. So you can't just use equals as an immediate constant in your assembly code. So you have to load that value into a register first. So in this case, for the locked mutex code, I just ended up loading the locked value and the unlocked value into R1 and R3. And then you try to load the value from the argument that's being passed in through R0. If you remember, the mutex lock call in atomic.c passes the pointer to the unsigned integer mutex lock. So that's an address, and you try to do an exclusive read on it. And then what you do is you compare R2, which is the value that you just read, to the actual unlocked value, right? So here, you want to make sure that before you lock the mutex, that the actual value is unlocked so that you can gain the lock on it, essentially. So once you're able to do that, then what you do is, this is if you remember the conditional mnemonics, where this is actually a store exclusive if equals. So what you're doing here is you're making sure that it's unlocked, and only if it's unlocked, you try to write the locked value into the destination, which is your mutex lock variable, which is being passed into this function. So if you're able to read it exclusively and make sure that it's unlocked, then only you try to write the locked value and actually lock the mutex. And then, as I pointed out earlier, the store exclusive actually returns a value into R2, which is this destination register that tells you whether it was able to write successfully or not. And so what you can do is you can compare that and see if you were able to get the lock on the mutex. And if it's unsuccessful, which is, this is a branch if not equals, so if it was successful, it would have written a 0. If it's unsuccessful, it writes a 1. So you know at this point whether it's written successfully or not. So you can compare if it was successful. If it's not successful, it branches back to this label.l1 and then tries to get the lock all over again. So this is sort of following the logic that I have here for the pseudocode. And so once you're able to lock, unlocking should be trivial. You don't need to exclusively check if the mutex has been locked in order to unlock it, but you can. So I just chose to actually just write the value of unlocked. So same as I do in locked mutex, I load the unlocked value, and then I actually store that value directly into the argument that's being passed in. Here it's again going to be the same argument, which is mutex lock, which is an unsigned integer, the pointer to an unsigned integer. So I just write the unlocked value in there and then leave. So does this sort of make sense? This is just a poor man's mutex implementation, but I'm sure there are better implementations out there. So if you have any, please let me know. I'd be interested. The other interesting thing to note here is that the LDR-EX and STR-EX are a pair, which means LDR-EX actually, when both of these instructions are used, it marks the physical memory, saying that there's an exclusive access going on. And with virtual memory implementations on some of the SoC boards, it will actually mark the physical address, and the VMSA implementation has to take that into account, essentially. But those two are a pair, which means if you use LDR-EX, you can't use STR-EXB. you have to use LDR-EXB with STR-EXB and LDR-EX with STR-EX. Does that make sense? And as you can see, in between the LDR-EX and STR-EX, there's no memory access going on. I tried to load the value of unlocked before the LDR-EX occurred, and then I use it sort of in between. So now that we've covered sort of atomic operations, so this is the solution. It's slightly different. Here I actually use the constant directly instead of loading the unlocked value and checking if it's actually unlocked or not. So I just kind of hard code the value there. But I just thought it would be descriptive. And Ben actually had this question about how we can use assembly on the iPhone or Android. So for iPhone, from what I've read, apparently you can, the Xcode actually comes with GNU assembler, I believe. So you can actually compile assembly code and then use the .o files and include them in your project and reference the code that way. Or you can also use inline assembly. That being said, I haven't tried this out myself, so you can actually go ahead and try it out. And the iPhone ABI, there's also an application binary interface for ARM that's been specified by Apple. So there's a handy-dandy link for that. So for Android, it becomes a little bit more complicated. So Android comes with something called a native development kit, which allows you to run native binaries in conjunction with Android applications. So what you have to do is first get their toolkit. It actually comes with a bunch of cross-compilers tools as well as native development tools for hooking things up to Android applications. So first what you do is you actually write a stub code in C, just regular C that calls the assembly method like we did with our atomic lab, right? But the method has to take a specific number of arguments, and you have to use JNI types. So there's something called JInt for an integer that's 32 bits long. So you have to be wary of the ARM data sizes and compare them with the JNI type data sizes, and just use the appropriate data type. So once you have done that, you can you actually can copy a template makefile that's available for Android NDK, and then compile this C stub code with the assembly, and it generates some static objects. And then what you can do is you use the NDK tool to actually build, and using that, all that does is it uses the makefile to build the actual objects. And then finally, in the Android application, you declare a Java function with the label native. And it's going to be the same method name as your the one that you use in your stub C code. And the package name, interestingly, when you declare this C stub code, you actually have to give a unique function name that includes the package name. So I can actually show you an example here. So this link actually has much better information on this. But you actually embed your package name into your JNI C stub. So here, as you can see, actually you can't see yet. So here, you would give the package name followed by the actual function name. So you say Java, COM, Eggwell, Android, and that's sort of the package it shows up in your Android application. And so you just say package followed by com.eggwell.android.assembly, in this case. And so once you have that, you can actually declare this function using the native keyword, and then you have to also load the library using system.loadLibrary, and it loads the native library, and then you can make calls to that method, essentially, in your Android application. Does that sort of make sense? So Ben is asking what the Apple URL is. I've actually posted this with the slides in my transfer folder. So it's actually developer.apple.com, library, iOS, documentation, Xcode, conceptual. Yeah. So with that, I've also included some useful links, and this sort of concludes the class. So in retrospect, we kind of we started off with sort of what happens at power on with these ARM boards. You enter the reset mode, right? You're in supervisor mode, and then you start executing, generally it's the bootloader, at a specific address. And once the bootloader loads, then it runs the kernel and loads the RAM disk, starts running that, and then you can run whatever OS on top of the kernel, whether it's Android, Linux. And then we sort of went through what the assembly operations are, and we went over how to use GDB essentially on ARM. And finally, we looked at how buffer overflows might work and sort of the calling convention that ARM uses for parameter passing. And we also looked at atomic instructions and how interrupts work. So are there any questions? And we also looked at how to use inline assembly and how to reference assembly code in C. So you guys should be ARM programming machines now. Also, please feel free to send me any suggestions, corrections, or ideas that you may have.